if you guys remember, I'm doing a Corotation shell for formulation of, and I'm comparing the Castellated and regular I-beams. And I last time a few weeks ago I was doing the kinematic formulation, but then I kind of omitted the finite element formulation. But I'll just go over that today, just how the code is, how I'm doing that. And then I was able to get something for the static, so I'll show that. And then for the abacus, I'll show you guys some results from dynamics, and then buckling. But before that, I think I remember that there was a question on the elemental stiffness, and I did some reading on that, so I finally have an answer. But I think what it is so after you do all the formulation, and then now I'm going through the finite element. One of the advantages of doing a corotational formulation is we can actually reuse the linear finite elements, and I guess this means like using the same linear stiffness matrix, this KE right here. But then, and that's why so we're able to reuse that. But then now we're doing large rotations and small strains. So I was only able to I did code it, but then the thing is I was only able to write the equations here for the 3-node, but then for the quadrilateral, they're pretty much the same. But so I'll just go over the 3-node. So the triangular shell elements, mainly what the 4 steps are is you have, as I mentioned, you can reuse the linear finite elements. You can use the same shape functions as what you do for linear, but nonlinear in this case. And then I'm also gonna go over, like, since we're doing like shells, you're gonna have like 2 portions of your stiffness. You're gonna have the membrane, and then you're gonna have your bending. And then in the last part, this is gonna be where I'm gonna introduce this the corotation is how you, if you guys remember, I talked about how we have the shadow configuration, and there's different like algorithms where you're gonna have to fit the shadow with the deformed configuration, and I'll talk about that. And it just depends on like how you form a certain matrix. All right. So for the first, so pretty common with like when you're doing finite elements is this equation, where you have this K and times V, and you get their forces. So we'll do the same thing here. One of the main differences is you're gonna have these basic and then high order stiffness. So that's what this KB and KH are. So I'll briefly go over these. So technically what I'm doing here is I'm just doing the boundary tractions, and then I'll formulate the N matrix, which is like the shape or the shape functions. And then so the first one here comes out, and then this L is just it's like a form. I just lumped it into, so you have these like tractions. Now you're applying this shape function, so you're finding them at the node. So I'm just lumping it to this L. So that's what this KB is. It's just your basic stiffness. And now what I'm doing here is finding the second stiffness, this higher order. And like what this does is, as I read, is it just gives it more of a better performance. So how you do that is all of this. So in this KH term, you're gonna get this like strain, or like the B matrix. Like, so that's just kind of like a Jacobian of your shape functions, or like your strain gradient, your displacement gradients, your strains. And so this pops out. You're gonna get this KH term with all these terms, and so just to explain that this is what the dimensions that I'm using these as the physical coordinates, and you have the length of the element, and then you have the height, of this element, and then these are some vectors, the side vector and then the unit vector that you'll use for your tractions. And then so now we're going to formulate the membrane. So those were just the basic, like big, and then the higher order, but then there's different versions of those for membrane and bending. So these are your degrees of freedom. And from this, it's going to be similar, your basic, you're just going to have this, this thickness that's going to change this membrane portion. And then the higher order version of the membrane is, it's going to have some of these rotation terms, or they call it like drilling degree of freedom. And from this, all of this is just, I'm trying to partition these rotations into like, it's like deviatoric and then volume, but they call it mean. So we're trying to take out the deviatoric portions of those. So just to skip this over, after you do all of that, yeah, you're gonna get the high order stiffness from the membrane, which is this very similar to what it was generally. And then now the bending portion of that. So here again, this is the degrees of freedom from the bending. And then so the basic stiffness. It's similar. The only difference are you have these different like L that I was talking about, the lump matrices, which will be different for the bending. And then the next one is formulating the higher order bending. You're gonna have different B matrices for these. And altogether, this is the form that we'll use. And then I kind of modified that to this final form. All right, so now we bring in, so those were just finite elements, you know, just creating each K matrix. So we bring in the kinematics. And what I'm doing here is generally, as I said, like, how do you fit this shadow configuration with your deform configuration is by a rotation. It's just G matrix. I think I mentioned this before, but the G matrix is just trying to map your degree of freedom to this rigid rotation or motion. So it's just a mapping, but how this G is going to change depending on what algorithm you're going to use to map this. So the first thing, I'm going to talk about their advantages and disadvantages. So the first one is you could use like you could align each side of it, and here's just a pictogram of this. So just to explain, the dash lines are the shadow configuration, and then the solid is the deform. So you're trying to fit the dash to the solid. And then how this does it is through aligning with the triangle sides. The one thing about this is it doesn't give you an invariant deformation. So it changes. It's dependent on like how, I guess, where you start, or depending on the geometry. So, because as you see here. So we don't really want this. So the other method is using this least square fit. And this is the G for that. And so this is just a pictogram. So what we're doing here is instead of aligning the sides, you're gonna do some stretching. So you're gonna stretch the shadow to fit the deform here. But again, this is not that good because you're trying to. So if you remember, this G is a rotation, but then you're not really doing a rotation. You're doing like a stretch. So in the end, you're gonna get this like fictitious normal rotations. But at the same time, you kind of resolve this first thing because then it is invariant, but then you're still not doing a rotation. So I guess in the end, the third version is this G is from when you finally do a rotation, a normal rotation. And then this is what I did, but this gives you both, or it solves the problem of like giving you invariant rotation and then an actual rotation. Okay, so I'm going to skip this over because this is for the quadrilateral. But just to show you briefly the static. So here, if you remember, I did this in the results in Abacus. This was the for the Castellated, and then this is the Lagrangian, and then for the so this is pins. I'll go over here, and for the MATLAB. So for what I just talked about, those matrices, I coded that, and then I'm going to compare the results. So if you look over here, this was the exact, and then the Castellated. I increased the number of degrees of freedom, and then I got somewhat similar. So it's closer than what Abacus was giving me. And then even for stresses, so this is the strong axis. So if you look at like this, so this is the exact, it's about 42. And then this was giving me 42 as well. But the Abacus, maybe there's some kinks to it, but like it's really giving me like overshot what the exact was. But this displacement somewhat, but I think what's good is at least I was getting good results for MATLAB or the equations instead of using Abacus. And then now I'll just go over the Lagrangian results for dynamics and buckling in Abacus. And I was doing, just for fun, I guess, what I did was I used another software and it's plot, like a modeled so what you're gonna see here is, I guess, just a comparison between like the Castellated model in Abacus and then another software that I did for the regular beam. So, and then just to see if Abacus can, in essence, what I'm doing here is just a parametric. I'm trying to confirm if what results I'm getting from Abacus is good. So I think this will be good to use in our software. So for the fix regular I-beam, and then so this is dynamics, linear dynamics. I'm only doing the mode shapes. So this is what I'm getting. I'll show you guys the numbers after. And then for the Castellated, kind of similar mode shape, you get first band. And you're gonna see the second mode shape for the regular. So you're gonna get a second band, and then for the Castellated. And then I guess the behavior is kind of similar to what we saw in the static, where since for the Castellated you have a lot of the perforations here, you're reducing the stiffness, so that reduces it increases your vibration because the stiffness is reduced. And for the pin, your first mode is kind of similar. And then for the Castellated, and then the mode shape for the second mode shape, second band. And then this is the other one for the second mode shape. And then you're gonna get a third band for the third mode shape. And then for the Castellated. And then the last band, you're gonna get a fourth band. And then the Castellated. Okay, so these were the results for just the quadratic, and for the regular, and what you saw, these are just the numbers for it. So I think I have the exact number, but then I'll just tell you here. So what I did was I had some frequencies and then period for all of those, and yeah, like what will be helpful is on my next presentation is I'll show you maybe like an error, like I'll calculate some percentage errors or change, and I'll compare these to. It'll be a better way to compare if we have like accurate results. And then for the buckling, these are from Abacus again. What I did here was just do. I didn't do it for the other one, but I'll just show you the results. So for the buckling, for the fix, this is what I got. So the loading case that I talked about before was in the static was transverse. But then for the buckling, it's going to be uniaxial. It's going to be here. So as you can see, the bends or it buckles out of plane. And so this is for the castellated. It's kind of similar. And then this is for the pin. And then the castellated. And then, okay, so the numbers show here, just looking at the abacus solution and what I calculated. Since this is just, we're just doing like the buckling load, they really overlap pretty well, like from what I got in the exact and then the finite element solution. For fix, and then for pin, it's about, it's roughly there, it's about 1%. All right, so next time I'm gonna finalize my stress concentration. I'm really interested in this because I wanna see like what type of stresses we get because of these perforations. And I guess I'll end it with some error plot and then some analyses on like as I refine the mesh, do my errors reduce, and then as I use like quadratic or versus linear, does it also reduce? So yeah, that's all I have for now. I'm hoping that I can finalize this in the next few weeks. All right, thank you.
Thank you. We'll hold off on any questions till the second hour so that we have some bathroom break in between. Okay. See you at 2.